Can you hear me?
Yes.
Okay, my name is Rick from Components Express. We manufacture machine vision cables. I only speak English. I'm sorry, I'm from Chicago, so hopefully everybody understands English. I wanted to talk a little bit about vision system validation. Primarily, how do we make sure that the cables we manufacture for machine vision meet the machine vision standards so that we don't have quality problems in the field, missing data, artifacts, and things like that. So there's a little bit to that. I want to talk specifically about some of the different machine vision standards and how we test for the cables for those. So I'll just read this. You can read it too. How confident are you that your machine vision system will operate without problems? The most underrated piece of a vision system, the cable, needs complete performance evaluation to ensure the user doesn't need to make a support call or have an issue. We'll talk about how the cables in each of the standards are validated, and we'll address that now. And I'm going to talk about 5 different standards. First, Cameralink, Giggy, CXP, USB3 Vision, and Cameralink HS. So the first thing is Cameralink. It's virtually important that the cables tested and verified to match or exceed the pixel clock requirement of the hardware being used in any one application. This can easily be done by doing the following, and we'll talk to that. So what we found is that all the cables, when we make them, we have electrical testing that we do. So we test them for continuity, we test them for pinning, that they're accurately pinned, and we test them for electrical characteristics. But what we found, especially with Cameralink, sends multiple streams of data over parallel lines. They're called taps in Cameralink, and sometimes it even uses multiple cables in the full configuration. It's a digital output, but there is no error correction in the stream of data that goes across. So we have to check to make sure that all the bits, all the data from the frame is getting to the other end in the correct order, and that it's not missing any bits, because the Cameralink standard itself doesn't really tell us if there's a problem. It's a real-time environment. That's why it's so fast. So what we do is we do BERT testing, or bit error testing. And the way we do that is we have camera simulators. These output a known test pattern that we know the bit logic of what's going out of the camera. And then we use basically standard frame grabbers, and we have a combination so we can test with both Cameralink MDR and HDR connectors. And we have frame grabbers for both MDR and HDR, and then also there's a special camera, there's a special mode called Deca mode where they actually use extra wires in the cable to get more data out on the cable. So we have a frame grabber set up for Deca mode as well to test. And what we do is we send known images over the cable several thousand times, and we check every single bit of every single frame to make sure that it got there correctly. The other thing about Cameralink is the cable uses different pairs on opposite sides of the connectors. So a cable may work in one direction, but if you actually flip the cable around, it might not work in the other direction. So we test to make sure that all the pairs work in all the directions. So we actually test the cable going one direction, and then we flip it around and we test the cable going the other direction with the bit error test. The second thing about Cameralink is that it has variable speeds. So it has a clock to the signal. The Cameralink standard has a certain frequency range. I think that it used to be at least 20 megahertz to 85 megahertz. But our testing hardware can actually do up to 105 megahertz. And what we found is that for a particular length, the megahertz can make a difference. So if a customer wanted to do a longer length, they might not be able to do it at the highest frequency. So we actually test at different frequency levels for bit errors as well. And we actually overclock the cables when we test them. So if a customer needs an 85 megahertz application, say 5 meters long, we will actually test that as 87 to 88 megahertz to consider it a pass. And that makes up a little bit for variations in the connectors and some of the other variations in the field that might happen. and we found that that works very well for Cameralink. So we have this screen here is just showing the testing report. So we keep track of the serial number, the length of the cable and everything, and then the system will actually run the test, and we can do a range of speeds, and then it gives us a test report and a pass-fail as we test the Cameralink cables. So let's go on now to Giggy. Giggy, well, I'll read it here. Simple verification test using off-the-shelf network analyzer, and I'll talk a little bit about that, which measures near-end and far-end crosstalk, return loss, and attenuation. The standard electrical point-to-point test is not sufficient, and that's kind of like I said with Cameralink and with all the cables. With Giggy, we're fortunate in the vision industry that Giggy is not just the vision standard, but it's a well-defined industry standard for networking as well. And because of that, there is, and we'll go to the next page, off-the-shelf electrical testers. These are testers that we use that I think are made by Fluke. And they can perform a whole battery of tests on a Giggy cable. They can check for crosstalk between the pairs. They can check to make sure that the twist on the pair is correct for each pair. They can do signaling comparisons, and it's like I said, very industry standard and a well-known standard, and we can address all that with doing the Giggy testing. But it's a lot more than just plugging it into continuity tests and making sure that it goes. I want to say too, if you have any questions, we'll talk about questions later, but if you have something immediately you want to ask me, I'm okay with that. Coax Express. So now with the release of the latest specification, which is the new Coax Express version 2 standard, which now can go up to 12 gigahertz, 12 gigabit, I should say, speed, there's a need for 2 different verification tests. So we need to test for both CXP6 up to CXP6 compatibility, which is the original Coax Express standard, and then also test for CXP12, which is actually 10 and 12 speed. The cables need to be tested and verified against the speed required for the chosen hardware in every application, in any application. So first of all, for CXP6, or the first version of Coax Express, which is basically CXP1 through CXP6, we have something similar to our Cameralink tester, but this time we use another camera simulator. This is the camera simulator that we use. And it's actually powered over the Coax Express. And then we have a standard frame grabber. And then we have software that sends a battery. The camera simulator will send out known images, test patterns, and then we check to make sure bit for bit that we're getting accurate data at the other side. And then this can do this in different speed levels. So it can do CXP12 or 1, 3, and up to 6 speed. This software will then give us a report. It'll give us error testing information to know if the cable did it, had a bit error or not. And basically, to anything we build, any bit error is not acceptable. So, and this is done by the length of the cable. So, certain customers' requirements, we'll test for the length of the cable that they need and make sure it meets the speed requirement. That's for up to CXP6. And then now for CXP12 and 10, we've got another setup. So this is actually an FPGA-based camera simulator for CXP12. It's outputting the newest CXP12 signaling. And then in this computer, we have a CXP12 frame grabber. And then we can, again, do a bit error test. We can run over a period of time, and we can count up and get a statistical confirmation that we're not getting any bit errors. And we do this for different lengths of the cables. But there's more that we actually do for CXP12, and I think that's the next slide. So CXP12 actually has some pretty rigid electrical standards for the actual cable itself. The attenuation of the coaxial cable, and then also the impedance of the connectors on CXP12 is very important to verify. So we have a device, this instrument here It's called a VNA. It's actually, ours is called an ENA because it's an enhanced VNA. VNA means virtual, is it virtual? I'm sorry, I don't remember the acronym. It's a network analyzer over time. So what this does is this sends a signal down the cable, and then it measures the reflections back into the machine. So it can test the attenuation of the cable. CXP12 has a standard, and it's kind of hard to see on the screen, but if you look closely here, maybe I can use the pointer. Different levels, different speed tiers have different attenuation requirements in CXP12. So basically the 12 gigabit CXP12 is really running, clocking the cable at I think it's 6.5 gigahertz speed. So we actually test the cable at, we look at the attenuation at all the different tiers for the different CXP speed tiers, all the way down to CXP1 speed, which is like 512K speed, actually, this level here. And then it measures the attenuation. And then we do this for different lengths of cables, because what we found is that once you get past a certain length, the attenuation of the cable, the reflections will increase to the point where it doesn't actually meet the spec. Now, sometimes a cable will pass the bit error test, even if it's longer than it meets the CXP test. But when we build the cables, we actually use the CXP standard because it's very well defined for testing the CXP cables. So then USB3 Vision. USB3 Vision is kind of interesting because what the vision industry has done is kind of take an existing consumer standard, the USB standard, and they've tried to enhance it in different ways to use it for our applications in vision. Some of it are mechanical requirements for screws and locking the connectors and things like that. But there's also, they're trying to increase the lengths of some of the cables, and then there's some USB3 Vision applications where they're not actually doing all the handshaking for USB 2, they're just strictly using USB 3. So we do a couple different things to check the USB 3 cables. So the first thing that I have is, oh, sorry, I hit the wrong button. Let's go back here. One more. Okay, this button. So this little device here is actually a loopback device for USB 3. And what it allows us to do is we have a USB 3 port in our computer, and we can actually send packets of USB data down the cable, and then this device actually loops that signal and sends it back down the cable. So we can do both directions, and we can test this, and we can do it at different speed tiers. So we test all the USB 3 Vision cables at the full 5 gigahertz spec that the USB 3 Vision standard allows. And it's very important. This device also can check the voltage and the current at the end of the cable. So we have to make sure, because USB is a powered application, we have to make sure that the cable will support the power requirements for the USB at the end for the camera, and that it can support the voltage that was required at the end. The main reason why we go to great lengths on this is because the people are trying to go great lengths with the USB cables. They're always trying to go longer and longer with them. So we need to make sure that the USB meets all those specs. But in addition to that, we also do live testing with the USB 3 cables. So USB 3 is, we have a whole series of different USB 3 Vision cameras, and we do real life tests with the USB 3 Vision cameras, because there's a little bit of variation in some of the different implementations in USB 3 Vision that we found with different manufacturers and different combinations of both cameras and host adapters in the machines. So we try to test the widest range to make sure that we're getting an accurate signal. A lot of the USB 3 Vision applications can do air testing as well, with test patterns and things like the bird testing. Then we do something similar to the other products with with Cameralink HS. Cameralink HS can go, was it 5 gigahertz or 10 gigahertz on copper, and we have a similar setup to we do with the standard Cameralink. In this situation, these frame grabbers that are in the machine are actually FPGA-based frame grabbers. And because Cameralink HS has both an input and an output, we program one of the grabbers to be a camera and a camera simulator, and then we program the other frame grabber to be a grabber. And then we run special software that we send known images over the cable on all the lanes, so that they can go up to 7 lanes on a single cable. And we can get a test pattern, and then we can check for bit errors. I think there's another screen here. So this software will actually give us statistics on what happened. I know it's very hard to read. And this software can actually also do something called an eye pattern, where you can actually test and see that on all the lanes how wide open the eye is for the different tests. And that's pretty much what we do for these different standards. Is there any questions?